Good morning, everyone. Today I'm very excited to talk to you about our work, making logic a first-class citizen in generative ML for networking. And this is a joint work with Minhao Jing and our advisor, Maria Apostolaki. So GenAI has been proposed to support a variety of networking tasks. For example, traffic synthesis, telemetry imputation, resource allocation, and so on. And in this talk, I will use telemetry imputation as an example. But our approach generalizes to other tasks, as we described in our paper. Telemetry imputation takes coarse-grained network signals as input and aims to impute their fine-grained network counterparts. While GenAI has become increasingly powerful, its probabilistic nature means it still makes mistakes. For example, the imputed ingress bytes could be even larger than the bandwidth. And the imputed values could not add up to the total value, which is another mistake. And it can also generate values, small ingress values, which contradicts the congestion signals we observe from the network. And we can formulate these mistakes as violations of fundamental logic rules. For example, the first rule says the ingress bytes should always be bounded by bandwidth. And the second rule says the imputed bytes must add up to the total ingress. And the last rule says the burst would imply high link utilization. And in fact, in practice, we've seen a lot of rule violations, even for state-of-the-art data generators. So in this graph, on the x-axis, we have a rule violation in percentage. On the y-axis, we have different ML-based data generators. As you can see, they violate large numbers of rules. And even for network-specific frameworks, they are not necessarily doing any better. Only NetNomos, which is what we are proposing in this work, can achieve zero rule violations. So the natural questions we are asking in this work is, first of all, how do we obtain these rules? And secondly, how do we impose these rules? So in terms of rule learning, there's a natural trade-off between the expressiveness of the rules and the scalability of the rule learning process. As a human, I can write whatever the rules I want, so I am very expressive, so to speak. But I don't want to sit there all day long writing rules, so I'm not so expressive. Alternatively, we can use data profiling methods to profile data using some database methods to get integrity constraints, for example. But this approach doesn't support the complex network rules we need for networking. Alternatively, we can treat the entire network as a distributed system consisting of hundreds of network devices. And we can use protocol inference for distributed systems to get a set of rules. And this is attractive because this supports expressive first-order logic, but unfortunately, it wasn't designed to scale to millions of packets we have. In terms of the second research question, there are two approaches to helping ML follow rules. And we can either do it proactively during training by encoding the set of rules as additional loss terms on the objective function. Or we can do it reactively, only correcting the mistakes once they've been made. Unfortunately, on the training side, this approach is limited to differentiable rules. Otherwise, we cannot add them to the objective function without doing some approximation. And it doesn't scale if we have hundreds of rules. And most importantly, the behaviors penalized during training can still appear at inference, providing no guarantees. And this can be a costly process if the rules we want to impose have changed. And we need to retrain and fine-tune our model again. On the other side, to correct the mistakes made by the GenAI model, we need to define some metric, the cost metric, to be minimized during this correction process, so that we can preserve the originality of the output as much as possible. Unfortunately, the semantic distance between network data points is hard to define in networking. And this process inherently overrides the learned data distribution by the model. So to encounter these challenges, we propose NetNomos. NetNomos supports expressive and complex network rules and learns them in a scalable manner to millions of network data points. And it automatically selects relevant rules based on the downstream tasks and enforces hundreds of rules during inference. So let's start with the first stage. In terms of rule learning, we want to place NetNomos at the top right corner of this trade-off space because we want both expressiveness and scalability. And the key insight that allows NetNomos to achieve this is a normal reformulation of the problem as constraint modeling. And we've all seen systems of equations from high school, and we can get a set of feasible points from the constrained set of equations by using, for example, Gaussian elimination to reduce them to echelon form. But if you think about it, the network can be seen as a constrained data generation process. And the resulting data points are the feasible solutions to that constrained data generation process. So the goal of rule learning is to map those resulting data points back to the set of logic rules governing the data generation process. And this process and this reformulation allows us to reduce the problem of learning expressive rules to finding minimal hitting set. A rule is consistent with a data point if that data point satisfies that rule. And by definition, all data points should satisfy that rule, otherwise the data couldn't have been generated under that rule. And a rule consistent with all the data points is a hit, and our goal is to find all such hits. But the space of all possible formulas is infinite. So we want to design the grammar, the rule grammar of NetNomos specifically for network data. We call it gamma, expressed in first-order logic grammar. Next, I will use R3 that I talked about earlier as an example target to quickly explain how NetNomos learns rules. First of all, NetNomos will populate the predicate space in first-order logic. So you can think of those predicates as the strongest assertions. So for example, the first predicate says there's always congestion. The second says there's always no congestion. And I'd like to highlight here is that unlike prior work, this enumeration happens not for the entire formula space. It happens only for the elements of this formula space. And then it projects those predicates onto propositional literals. And you can think of those literals as even smaller atoms of this formula space. Then NetNomos builds evidence sets. So an evidence set is a set of data points that satisfy a specific literal. So in this case, for example, the first literal is satisfied by one data point, and the second is satisfied by two data points, and so on. And again, this enumeration of all the data points happens only once instead of repeatedly. Next, given the evidence sets, NetNomos searches for minimal hitting set. A hitting set is a set of propositional literals whose evidence set together hit all the data points. And by minimal, I mean this hitting set is not a superset of any existing hitting set because we don't want redundancy. And then NetNomos takes the disjunction of all the literals in a hitting set as a learned rule because this rule is a hit. Why is that? Because all the literals in that hitting set together satisfy all the data points. So by definition, it is consistent with the data we have. And in fact, we've learned our target rule because R3 is equivalent to this rule in first order logic. So I've introduced the first component of NetNomos. I will refer you to our paper for the second component for the time constraint we have. And I will quickly introduce next the rule enforcement of NetNomos. So NetNomos enforces rules not reactively or proactively. It does it just in time, during inference. So to explain how this works, I will use the rules I introduced previously, R1 to R3, and I will simplify those rules by assuming that a monitoring window to be 5, a bandwidth to be 60, the total ingress value to be 100, and we did observe some congestion signals as ECN mark bytes. So given the set of rules we want to impose, R1 to R3, I want to use a GenAI model to impute the fine-grained ingress bytes I0 to I4. So in this case, I'm using a language model. So what the model will do is that at every step, it will impute an ingress value. But as you can see, it already made a mistake by producing a value larger than the bandwidth, violating R1. And in fact, from that point on, it's no longer possible to satisfy R2 anymore, because the values don't add up to 100. So instead of correcting the final output of the language model, NetNomos enhances the inference process itself. So alongside the language model inference path, NetNomos also runs an SMT solver. So given the set of rules we want to enforce, the solver will tell, okay, given R1, the ingress values cannot be negative, crossing out the negative values. And the language model can only choose from the valid values highlighted in green. And the partial output of the language model is fed back to the SMT solver. The solver computes the feasible region for the next value, I3. And it crosses out the invalid values. The language model can only choose from the valid values. And the process goes on until we compute the final value. In this case, we have a global constraint R3, so the final value is only, there's only one feasible value. And we can guarantee that the final output of this process is rule compliant because we are enforcing the rules at every step of the way. And it was still the language model that was making the decision given the learned data distribution among the valid values. So it preserves statistical fidelity. And this graph demonstrates NetNomos in action by showing ingress bytes over time. So the blue area represents the feasible region computed by NetNomos at runtime. And the right lines represent the real ingress values, which are always within the feasible region by definition. At the bottom, I'm showing the output of Zoom2Net, which is a state-of-the-art data imputer. And as you can see, it constantly hallucinates impossible values exceeding the feasible region. In contrast, NetNomos, which I'm showing at the top in blue, always guarantees that the imputed bytes are always within the feasible region. So to evaluate NetNomos, we raise three evaluation questions. First of all, how expressive and scalable the rule learning algorithm really is in practice. Secondly, can NetNomos actually filter out meaningless rules with high precision? And lastly, does the rule enforcement mechanism of NetNomos provide guarantees of zero rule violations and achieve high statistical fidelity? Given time constraints, I will give some quick summaries of the first and last question, and please refer to the papers for more details for the second question. To evaluate the expressiveness of the rule learning algorithm, we curated benchmark rules, benchmark rule sets from RFCs, protocol documents, and so on. And we use coverage as a metric on the x-axis. Coverage is basically the number of rules learned by various learning frameworks showing on the y-axis over the total number of rules in that benchmark set. And as you can see, NetNomos can express and learn all the benchmark rules, while other methods fall short. To evaluate the scalability of the rule learning algorithm, we still use coverage as a metric, showing on the y-axis. And the x-axis is the learning time. And here, we're comparing NetNomos with DuoAI, which is a state-of-the-art protocol inference algorithm for distributed systems. And NetNomos scales much better compared to DuoAI, learning a lot more rules within the set time frame. To evaluate the rule enforcement component of NetNomos, we use GPT-2 as the backend GenAI model, and then we train the model on Meta's data center dataset, and then we evaluate the same model on 3 downstream tasks: telemetry imputation, traffic forecasting, and data synthesis, by enforcing 3 sets of different rules. And NetNomos guarantees no rule violations for all of them. And here's a quick summary of the results. First of all, in telemetry imputation, NetNomos improves upon the vanilla GPT-2 model and performs on par with Zoom2Net in terms of both imputation accuracy and downstream tasks. And in terms of data synthesis, it performs better than a whole host of data generators like NetDiffusion and NetShare. So in this work, we propose NetNomos that makes logic a first-class citizen in generative ML for networking. It supports expressive and scalable rule learning, and it provides high statistical fidelity while guaranteeing no rule violations. And they can repurpose the same language model for different tasks without retraining. And we've open sourced our code with detailed documentation so that you can try that out today with our favorite language model. With that, I'm happy to take any questions. Thank you very much.